Okay. So in the last class, we were here at this gradient descent. So we started this, and you know that what is the purpose of using this gradient descent. So gradient descent is the algorithm which will help you to update the W. So that's the purpose of the gradient descent algorithm. So if you have W, past W, the previous W, so you'll just your formula would be W new equal to W old minus alpha of your del L W. That means the gradient of L with respect to W that you need to calculate, and then multiply with the learning rate, that is your alpha. It is also called a step size, and then you subtract this matrix from this matrix, and you know the logic like we already have seen in the last class. Okay, so now this is called gradient descent. Okay, so whenever I'm saying gradient descent, that means it is happening, it's like general formula. So here, like, we are providing all the samples at a time. We're just giving, suppose we have to train the model. So what I'll do, I'll just take all the samples from the training data and will give to the gradient descent. Okay, and then what it will do, it will find the loss, average loss, then it will find the gradient of the loss with respect to W, and then there will be old W. So it will subtract that value from this, and finally it will give you new W. And this will happen for every epoch. So like every iteration. So in a iteration, you will do it, you will get the new W, again go for the next iteration, take this new W as a old W, and again you multiply with all the, like, you just take all the inputs, all the samples, get the loss, and again you do it, again you find the new W. So this will go for n number of times. So iteratively it is happening. Okay, so now gradient descent, whenever I'm saying gradient descent, that means I'm providing all the samples, all the training samples at a time. But in real scenario, you cannot give all the samples at a time. What the problem? The problem is that we do not have that amount of memory. Because if you're providing all samples to the network, that means I should be having that amount of memory. Then only I can store all the samples and will process it. But you do not have that amount of memory. Okay, so this giving all the samples is not the good idea. So what we do, if we do not give all the samples, then what should we do? Let's go for giving one sample at a time. Take one sample from the training data set and give to this W, and then W will find the loss, and then your loss will back propagate, and again you will get this gradient, you will update it. So what you are doing, you'll update this one by one. One sample, update it, another sample, update it, another sample, update it. So it can be done. And every time we are taking the random sample. That is called stochastic gradient descent. Stochastic means like randomly we are selecting. But the thing is, if you are providing one sample at a time, because if you are giving one sample and then you are changing the W, another sample changing the W, another sample changing the W, what will happen? The first thing is like it will be very, very slow, because you are processing n number of times, even for the one iteration. The second thing is, while doing it, maybe one guy would be very, we can say, he would be naughty guy or maybe a bad guy. So if the guy is bad, or maybe one sample is bad, then that may affect the gradient, or that may also affect the W. So suppose you started from here, going here, going here, going here, and suppose one sample comes here, and then what this sample does, it will just divert you from the actual path. Okay, and it can happen multiple times. So once you diverted from here to here, again you have to come here, because anyway, like, you have to follow this path to reach the minimum point. But since some samples are bad, So that may create problem if you are going one sample at a time. So if your training is happening sample by sample, then it's the problematic thing. Okay. So then why not we should choose the some mid-level idea. So we know that we cannot go with all the samples. We also know that if we go with one sample at a time, that is also problematic. So let's go with batch of the sample. So in general, whenever you will be going to train your model, you will be training your model in batch. So what you will do, whatever training samples you have, maybe you have n number of training samples, you will divide these samples into batch, and maybe you will decide the batch size. So batch size may be 32, 64, like it's your choice, whatever number you want to. Again, it depends on the memory also. So if you have good GPU memory, good amount of GPU memory, then you can go more number of samples in a batch. But again, your memory will restrict you this batch size. So whatever batch size you are taking, divide by it. Now this will give you total batches. And now you process one batch at a time. So whenever I'm saying one batch at a time, that means you process one batch, find the gradient, find the loss, find the gradient, change the W. Then go for second batch, again do the same thing, update the W. So every batch is changing the W. Okay, in the case of, it is called mini batch stochastic gradient descent because we are going in a batch. If you are going with simple stochastic gradient, naive stochastic gradient descent, that means you are going one sample at a time. Okay, so every sample is changing the W. And if I go with a gradient descent, simple gradient descent, then I will be going with all the samples at a time, but which is not possible in a real scenario. Okay, so I'll come to this slide also where we have explained all the things. But before that, we have another slide here. So suppose in the W, we have two values. You could be having any number of values, but let us assume that we have only two values. That means we need to learn only two values in the W, which is W1 and W2. Okay. Now, this is the magic box that you have to learn because your input will be multiplied with this, and then finally you will be getting the score, or finally you will be getting the loss. Okay. So if I plot this thing, because this is in the 2D space, so I can say I'll be having W1 in this direction, W2 in this direction. Okay. And initially you will be given some value for W1, some value for W2. This is like the initial value that is being taken from somewhere, maybe from some distribution. Okay. And then that is the starting point. So suppose you started from here. You took the one value of W1, one value of W2, and one just random value. And this you started from here. Okay. Now you have to move in such a way so that you should reach here, because this is the minimum point. It's the red color. Okay. So you start from here, and you will be moving, and finally you have to reach here. So that's the goal. Okay, so I'm just showing you the visual representation of this, like how it is happening. So you will start from somewhere. Maybe this is the starting point. And then every time you will be getting the loss, finding the gradient, and changing the W. And your W should move. That means your W should be changed every time. And it has to change in such a manner so that finally you will be reaching here. And what is this? This is the point where your loss is close to zero. That's the goal. Okay. So in 2D space, this is the visualization of the W that we are working on. Okay, so I said that we go with mini batch stochastic gradient descent. So stochastic is involved because this is like probability is involved, because we are randomly selecting the samples from the training data set. So we have all the samples here, and randomly we'll select from randomly will select some samples from here. So if you are going with a stochastic, then we'll be selecting one sample at a time randomly, but that is not the good idea. So we go with the mini batch. So we take randomly n number of or p number of samples from here, and that is like one batch, and it will be given to the model to learn. So your model is W, so that will learn. So if I just if we just see the code, so code would be this. So you can easily write this code in Python. It's very simple. So now your data is this. So now what I said that you have to take the one batch samples at a time. So this is the data, full data. And suppose we are fixing the batch size 256. That means we are going to take 256 images at a time. And those images will be coming randomly. Okay, so this is the function that we'll be writing. And it will take the 256 samples at a time. But every time it will take the distinct samples. They should not be overlapping. Okay, so if it is taking 256 samples, now once it is came out from this data, now next time it will not take same number of samples or same samples. Okay, so that we have to somehow ensure. So like it should not take the repetitive elements or the same elements, same samples again and again. Okay, so so it will give you the data batch, and then this data batch will be given to the evaluate gradient function that we already have seen. So again, this part we are going to see in the next class, like how to find the gradient, because we like in the last class we just talked about the numerical gradient, but I told you that we are not going to use numerical gradient. Instead, we'll be using the analytic gradient. So that part will come later. But let us assume that this function is given to you. So what this function will take? It will take the loss function, because you have to find the loss. It will take data batch, the number of samples that you are giving to this this W at a time, and it will also take the W weights, and then it will multiply W into X plus B, find the score, then find the loss, and then find the gradient of loss with respect to W and bias. So let us assume that, let us ignore the bias for now, but again bias will be always there, but let us, for the simplicity, let us ignore the bias. So it will take the, it will get like it will calculate the loss, and then your loss will be like you have to find the gradient of loss with respect to W, and then that will be returned here. And you know now how to proceed further. So what we'll do, I'll just take W equal to W minus step size into this. That is your del LW. This is the same thing that you have calculated here. So you can see in the next line, the same thing has been written here. This is the same thing. This different way of writing, but both are the same thing. So W equal to W minus step size into the gradient of L with respect to W. So now you'll do it. And again, you'll be doing this thing for every batch. So first time you'll take the first batch, then second batch, third batch. Once you are completed all the batches, that is called one epoch. Okay. And or we can say one iteration. And then again you'll go for the next iteration, next epoch, because one epoch is not sufficient. Just showing all the images once is not sufficient. You have to show the same image again and again in multiple epochs. So in a epoch, you can show one image only once, but again, you have to show that image next time in the second epoch. Because second time we have the different W. So in a epoch, you got one W, one very good W. But that is also not the best W. And you are searching for the best W. So you got the good W in one epoch or one iteration, where you have shown all the images, all the batches. You got one very good W, but this is not the best W. So you have to seek, we have to search for the best W. And that's why you have to go for the multiple epochs or multiple iterations. Okay, so we have seen like everything is good. We got the gradient descent, which is the helper, and it will help me to get change in the W. And that was the goal. But you know that every technique comes with some pros and some cons. So stochastic gradient descent is very, very good algorithm, but it is also having some limitations, some cons. So let's go for looking the cons part of the stochastic gradient descent. So we could be having this type of situation also in the stochastic gradient. Okay, but before that, uh, okay, so this is not talking about the problem. It's just talking about the suppose we have W1 and we have W2 and you are here. This may be your starting point, and you have to reach to this smile, this emoji. Okay, so this is the final destination. That means it is the lowest point. Here your loss would be zero, close to zero. So you start from here and you reach here. And suppose you have only two W's in your W, only two values in your W. So you started from here and so you started from here, but you are going in this way. What does this mean? This mean this means when you want to change the loss, like goal is to change the loss. So whatever W you got, it has to reach to here. And once it reaches to here, that means your loss is close to zero. So now it just started, but it's going in this way. So if you can see here, you can observe here that in this direction, your W is changing a lot. Drastic change. One you got here, again you have reached here, again you reached here, again you reached here, again you reached here. So there's a great change in one direction, in W2 direction. Okay. But if I see in the W1 direction, in the W1 direction, there is no much change. It's very, very slow. It's very, very slow. Okay. So in one direction, it's very, very fast. It's going very fast. Your W is changing very, very fastly. But in another direction, your W is changing very slow. And due to this direction, your convergence will be slow. That means reaching to this point will be very, very slow. So this could be like one type of problem. So since you are not controlling the W, the value of the W, so you could be having this type of scenario that one W is changing a lot, but at the same time another W is changing only small quantity. And that may create the issue because overall it has to reach here. And if I want to reach here, there should be like a proper or equal amount of change in both the directions so that I'll go here fastly. Okay. But due to this situation, again, this will hamper the progress. Okay, and your convergence will be slow. So this is one type of problem that you may occur in the case of SGD. Okay, so this is one problem. Let's go for another problem. Another problem is local minima. So you started from here. Suppose you started from Manali and you want to reach Delhi or maybe Chandigarh. So Chandigarh is the minimum point where you have loss equal to zero. But in between, maybe you reach somewhere, and it could be Sundar Nagar, where what you found that we have like this plain region. So if you have started from here and if you found plain region here for a longer time, then what your model will assume that this is the global minimum, and it will stop here. So your model may be, or your model can be trapped in the local minima, which is not the actual minima. But since this is like this is like plane here, so if you find the gradient at this point, this will be 0. And you know that like by using gradient, you can like you will get to know like whether this is a global minima or low, whether it is minima or maxima. Okay, so that can be done using the like by using this gradient formula. So it will mistakenly it will assume this as a global minima, but in actuality there is global minima sitting somewhere here. Okay, so this type of scenario also can happen when you are solving. It is like general problem in for every optimizer. This is the general problem. So one problem is local minima. You can trap in the local minima. And another problem of the similar type is saddle point. So saddle point is the point which is looking minima from one side and maxima from another side. So if you just see from this side, suppose you just take the example of Sundarnagar. So if you are seeing the Sundarnagar from this side, it is looking like a minimum point. But if you are seeing the Sundarnagar from the Chandigarh side, it is looking like a maximum point. So that is your saddle point. Okay. So one maxima from one side, minima from one side. So again, this is also the problematic case. So whether you can get local whether you can trap in the local minima or you can trap in a saddle point. And this is very, very common. Saddle point is very, very common in high dimensional space. So if you are projecting to the high dimensional space, there many times when you are doing the optimization, you can trap in saddle point. So saddle point is like, we can say there, it's like enemy for you because it will hamper the progress, or it will stop the progress, because your model will assume that this is the point where I wanted to reach. But in actuality, that's not the point. You trapped. Okay, so this is another type of problem. Now we have one more problem, and that is gradient noise. So what I said when we started, that at that point I said you that we should not go with one sample at a time, because in a class one guy would be noisy, or we can say like he would be bad guy. So suppose in my class, in this class, if I'm taking consent for something, and if I'm asking every student, but at a time I'm just asking one student, and then I'm taking some decision. So every time I'm taking the decision, so this is me and I'm taking the decision. But how I'm taking the decision? Based on the consent, based on the information that I'm getting from the student. But what I'm doing, every time I'm asking to one student and then I'm taking some decision. Again, I'm here. Again, I'm asking to another student, I'm taking the decision. Again, I'm asking to another student, I'm taking the decision. So this was like, this is a good approach. But since I have to take the bigger decision, and if I'm going one by one, then this will be slow. That is the one problem. But another problem was that maybe one guy from these all the students, or maybe few guys from these all the students, would be the bad guys, and they may disturb me from the actual from taking the actual decision. Okay, so that was the problem when we were going with the one sample at a time. Now it could be possible for the batch of samples also. Suppose this is the batch, like your batch. So I'm teaching to your batch, Now, maybe it could be possible that every student from your batch is bad guy, because I have taught multiple batches. So I have taught all the previous batches and they were good. So if they were good, I got to, I took the good decision because of those guys. And somehow I reached here. Now, once your batch comes, now everyone from your batch is bad guy. So what they will do, everyone, since I am going with batch, so even if I take batch, since the objective of everyone in the batch is same, so what they will do, they will just disturb me from the actual path. So they may divert me maybe in some other direction. So this is also possible for the batch. Okay. And this is called noisy gradient. Okay. So one batch can provide, because you know that one batch at a time you are providing one batch, and then you are finding the loss and the average loss, and then you are calculating the gradient. So that full gradient would be noisy because of these all the bad guys, or because of these all the samples. So in our case, we will be having samples, all the images. So maybe we could be having all the noisy images or all the bad images, which will give you wrong or noisy gradients. And if you are getting noisy gradients, because you know that this game is based on the gradient only, that's why this is gradient descent. So if your gradient is, you're getting wrong gradient, then that means your update will be wrong. Okay, because your W is updating based on the gradient. Okay, so this can be also, this can also possible. So what we have seen three problems that we may occur. One problem is this type of problem, either local minima or saddle point. Or you can have this type of problem. This is called poor conditioning. So maybe in one direction you are going very fast, in another direction you are going very slow. Or you could be having this problem where your batch would be bad batch or noisy batch, and that will give you noisy gradient, and at the end it will give you wrong update. Okay. So we could be having these type of problems. Now, how to solve it? Like you guys can give some suggestion here how to proceed. Sorry.
Okay, so now, so a small clarification, sir.
Yeah, please.
So in our last class we learned that W is made out of at least 10 samples, which we are going to compare with the input image.
I said that W will be matrix, na?
Matrix, yeah. Matrix.
Yeah.
It's a matrix of 10 rows actually. Okay.
Yeah. So the 10 into 3072. This thing we have seen when we were talking about the linear classifier, and it was getting multiplied with X.
X, yeah. And then we are finding the.
Yes.
We are finding the score, and from that score we are again finding the losses, and we are adding again to that loss we are adding again the gradient descent to make the losses more meaningful and come to a convergent point. Now in this class, you're only considering initially you said 10 samples. Now you're saying the batch of samples which consisting of maybe n samples or p samples out of n samples. What is that meaning?
No,
in this class you said that there are n samples are there. Out of n samples, I'll be taking p samples out from the batch in a batch wise, and I'll be calculating that with the x value. And I didn't understand that particular point.
Yeah, actually, you got confused with this W and samples. So W is the matrix that you have to learn. Okay, so suppose in this case, this size is fixed for the W. Now sample, whenever I'm saying sample, that means image. Okay. So in this case, it will be image. So here, like I have just given one image at a time. So X, that is like one image. But in general, when you are going to do this apply optimization, then you'll go with the batch of images. Like you'll be giving n number of images at a time, because you know that you have GPU, and all these operations, whatever w into x, this can be happen in parallel, because you can give maybe one image to one GPU and it will do the computation. Again, second GPU will do the computation. So simultaneously, every GPU can give you can take one x and it will give you the score or loss. Okay, and then you can find the average of that, and then you on the average value you'll be applying like finding the gradient, and then you will be applying this gradient descent for changing the w. Okay. So actually here I've said that like you can go one by one, but one by one is not good. This was just was just telling the example like how it is happening. But in real scenario, in practical scenario, we provide one set of images at a time, and we give to that means like this will be not 3072 only, it will be maybe n into 30, or maybe I should write p into 3072.
Okay, sir, I got your point.
Okay.
Sir, to handle a noise in a data, we can increase the epoch, and we can also handle the outliers. And for problem 1 and 2, we can use momentum based concept that Adam optimizer use.
Yeah, so momentum. So why momentum? Again, I'll come to that. So yes. So you try to give some answer. That's good. So again, yeah. So we'll go to solve all the problems. So we'll go one by one.
One solution for this local minima could be like maintain the minimas from the previous batch and compare. And if it is, whatever is the previous experience or previous local minimas, we will store it and we can compare those with the current batch. At least for whatever, maybe we cannot get into the future, but at least so far, whatever have been the global minimas, at least we can compare the current minima with those and try to push the model beyond that.
Yeah, so that we are doing actually every time, like here. But you suppose you trapped here for this amount of time. So that means suppose for 100 epochs you are getting same loss. That means like if you compare the previous, it will match. Like every time you are getting the same loss. So if you are getting same loss every time, maybe for 100 epochs, then how to decide like whether this then everyone will tell that no this is the global minima, because now we are not moving further. So how to decide the global minima? You'll decide the global minima based on the gradient, like whether it is changing or not. So if the things are not changing, that means your gradient will be 0. So once you get the gradient 0, that means now you know that this is a flat region. And once you reach to the flat region, you will assume that this flat region would be the global minima. And this is happening not for few epochs. It is happening for maybe for 100 iterations or maybe for 50 iterations. But let us go with step by step. So we'll solve one problem and then we'll go for the second problem, then we'll go for the third problem. Now let me just tell you, this is the global problem. So every algorithm, like whatever algorithm we have in this optimizer space, every algorithm is having goal to somehow come out from this situation. But this is very, very, we can say, this is not simple problem. So every algorithm tries to come out from this situation. They do a lot of things, but still this problem has not been solved fully. Because this is, if you have convex plane, if you have this convex plane, then you know where the global minima. You can easily find the gradient of this, and that will give you the global minima. So where the gradient gradient equal to 0, that is your global minima. But you do not have this type of a structure. You have this type of a structure, and that's why there is problem. So okay, so let's go one by one. So first we'll solve the first problem. So first we'll go to solve. Yeah, please.
Sir, like if the learning rate is very slow, like then will it skip the saddle point?
In any case, you may face saddle point. You may face local minima, because these things are happening in a high dimensional space. So whenever I'm saying high dimensional space, that means you are not in the image space. So in this case, like we have already transformed our image into some features. Like we have applied the linear classifier. So till now we have only seen the linear classifier, but once we go for the fully connected, then we apply multiple layer of the W, and that will project you in some higher dimensional space, like non-linear space, and there you could be having this saddle point. So that saddle point is very, very common in that space. So you may get this saddle point in any case. Did you get the answer? Or should I explain it?
Yeah.
Okay. Okay. Okay.
Sir,
So,
sir,
please.
sir, by any chance, maybe in the next class or maybe in the next week, can we take up this practical demo of this code, sir?
Yeah, I was also thinking that what we can do, like after completing the fully connected back propagation, then after that maybe we could be having one lab session. So that because in the lab, like if I go to implement fully connected, then I need all the things, all these components. So last component is still not covered. So that is your back propagation. So once I cover that part, then we'll be having all the components, and then we'll go for the lab part also. So maybe I'll take one lab session to explain like how the things are happening.
Sure, sir. Sure. Thanks.
Yeah. Okay. So let us go with one solution, and that is your SGD plus momentum. So first we compare SGD and momentum, and then we'll see like what type of problem this SGD plus momentum will solve. So we have seen 3 problems in past, and now let us see like which type of problem is going to solve using this SGD plus momentum. So this is the SGD that we already have seen. So this X is your W. I've just written in taking different symbol. So XT, so WT plus 1 equal to WT minus alpha del FXT. So this FXT is your loss function, and you're finding this the gradient of this with respect to W, and then alpha is learning rate, and then changing it. This is the simple SGD that we already have seen. I've just taken X at the place of this W. Otherwise, things are same. Now, in the case of SGD plus momentum, what we have done, we have just introduced one extra line here. This is the extra line, and that will go to play the major role. Okay. Now, in this extra line, if you see, we have Vt plus 1 equal to rho Vt plus gradient of Fxt. So this part is same as this part. The gradient of like this is same as like you're finding the gradient of loss with respect to W. But I have added one extra term here, and I'm just combining these 2 terms, and then I'm saying like this is my current gradient. So now I'm going to change the W with the help of this. So in the next line I'm doing the same. So this is your WT plus 1 equal to WT minus alpha of Vt plus 1. So initially, in this case, you had del Fxt here. Now, instead of that, now I'm writing Vt plus 1. That's the difference. And from where this Vt plus 1 is coming? This Vt plus 1 is coming from here. Okay. Now, what is happening here? Let us see. Let us just try to realize it. What is happening here? Okay. So what we are doing, this is the current gradient. Okay, let me just tell you one thing. If I say gradient can be considered as a velocity also, or speed. We should say velocity because gradient is having the direction as well as the magnitude. So that's why that can be considered as a velocity. And why I say velocity? Because it is changing the W. So your W is like, this is the W space. You have the W space. You started from somewhere from here, and every time your W is getting changed. Based on what? Based on your gradient. So gradient can be seen as a velocity because it is changing the W. So from you started from here, you reach 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 here, and finally maybe you have to reach here. So every time it is getting changed based on this gradient. So gradient is the guy which is changing the W, and that's why this can be considered as a velocity. Okay, so velocity is something which will change the location of the particular object. Okay, so W can be seen as an object, and its location is getting changed with the help of your gradient. So gradient can be seen as a velocity. Okay. So now here, so if I just relate this thing with this, so this part is also here. So this is like, this can be seen as a current speed or current velocity or current gradient. So this gradient is coming from the particular batch. So you started with batch 1, batch 2, batch 3, batch 4, batch 5. Now if I'm here, maybe at this point, what I'll do? Like the similar to the SGD, what I'll do? I'll just find the gradient of loss with respect to W for this batch. And that is this. It was also happening in the case of SGD. But now I have added one extra term here. And what is this extra term? This extra term is running mean of gradients. So this is the past information, or you can say past velocity, average of past velocities, or average of past gradients. So you started from here, you reach here, you reach here. Every time what you are doing, you are finding the current gradient, and you are also taking the running average of all the past gradient, or average of all the past gradient. And then you are summing these two terms. Okay. Now, what is this? How it will help me? How it will solve the particular problem? Are you able to realize it? So you are not going to rely on the current velocity. Instead, you are taking the help from the past velocity, past average velocity, as well as the current velocity. And you are taking the current velocity, like current gradient as it is, but you are taking the past gradient, the average of the past gradient. And that's why this rho into Vt is involved there. So rho is also called friction. So how much weightage I should give to the past. So this is not the simple average. So simple average would be like, if I'm here, I'll take the average of all the previous gradients, like from here. So this plus this and divided by 2, that will give you the average value. But I'm not taking all that average. I'm taking this running average. That means I'm taking weighted average. Okay. So I started from here, and I reach here. Every point, at every point, I'll be taking the past average value, but not simple average value. Instead, I'll be taking the weighted average value, or it is also called running mean of the gradient. And then I'll sum this thing with the current gradient that we have calculated for this batch. And this is the gradient that will change the W for the current batch. What I'm trying to do here.
Sir, what is the difference between normal gradient that we are deriving in the every epoch and then the weighted gradient or the
Normal means like for every batch you'll be calculating the loss,
yes,
you'll be
right,
calculating the gradient. So that is current gradient. Okay. So this gradient is related to this batch, like only these number of images. So it is coming from only these number of images. But you are going to train your model batch wise, na? So every time you will be getting a set of images, you will be getting the loss, you will be getting the gradient, you will be changing the W. And this is
right,
happening for every batch.
right.
So now what I'm saying that in the case of SGD, I was doing in that way. So for every batch, I was calculating the gradient and then I was updating the W. Now in the case of this SGD plus momentum, what I'm doing, I'm considering the gradient of the current batch, but at the same time, I'm also taking the average gradient from the past batches. Suppose this, let's just consider this
Yeah.
class.
So you mentioned that
So
it is not a simple average, right? It is a weighted average. So are we assigning
yeah,
weight to every batch now? Again, another W.
yeah. So first thing is like why can we consider the this simple average? Because if I want to find the average of the past, I just want to see like how the previous batches were doing. So I'm just finding the average of those all the information, all the gradients. So if I go with the simple average, what will happen? Because here what I said that I'll go with the running average. That means like I'll go with. So should I go with the normal average? If I go with the normal average, then what will happen? That's the question.
So every batch will get the same weightage.
Every batch
Previous
will get the
batch.
same
Every previous batch.
But suppose I started maybe from here, and I processed maybe 1,000 batches, and I have reached to here. Now at this point, your W is totally different, which has been shown here. At this point, this was like totally new, totally like naive W, and then it has been processed by every batch. And if I take average of all these, then this will be not good approach, because I don't have to give more weightage to these guys, because these are already now these were like totally new stuff, the starting point, and still I'm giving more weightage to the starting, like equal weightage to the starting point. Then it will not solve the problem. It will not give you the right direction to move. Why? Because at this point direction was different. Now at this point your direction is different. Okay, and now you are here. So at this point, whatever direction I have here, this direction may be similar to that only, but this will be not similar to this, because this is very far. So I'll not go with simple average. So we generally take the mean average, this running average. So I'll give less weightage to this, then less. Finally, I'll give more weightage to this, less. So I'm going to rely more on the recent batches and less on the past, like very old batches. So this is called weighted average. Okay. And then I'll take the weighted average of the past, and then I'll sum it. Now what we are trying to solve here, like we have seen 3 problems in the previous case. Now what we are doing here, which problem we are solving here? I put a lot of time here just explaining it. Now my question is why we are doing this? Which problem we are trying to solve here?
Saddle point or the local minima.
Saddle point, local minima, that's like general problem. So whatever we are doing, every time the goal is to
actual and predicted value जो भी हमारा पिक्चर है, हम उसके क्लोज जाना चाहते हैं, जो भी फिगर्स हैं, जो भी पॉइंट्स हैं, उसके
minimizing the loss, sir.
Yes, minimizing the loss as well.
That's the goal of every algorithm. Minimizing loss is the goal of every algorithm. But we have seen 3 problems. Just to recall all the problems. One was like this saddle point and local minima. And then second problem was your
batch.
uh,
Total batch was also.
Yeah. We are removing noise, sir. We're trying to remove noise, I think.
Maybe we are trying
Yes.
to find the best direction of slope.
Yeah, we are
Yeah.
trying to remove the poor conditioning, I think.
This was the one problem.
Problem
This was
number one.
another problem. This was the third problem. So poor conditioning, then local minima saddle point, then gradient noise. Which one we are solving here?
Poor conditioning.
Poor conditioning. How it is? Like how it's solving that problem? Poor conditioning.
Because we are reaching to the one point, and every time the noise is in, we are settling on one point with the very minimum deviation.
Okay.
That is,
Yeah.
I think.
Oh, okay.
One
Let me just give you the
solution would
answer.
be, since we are going for running average, okay, so the divergence or the convergence won't be very much high, and we can minimize it, and we can reach
Yeah.
to a destination much quicker.
Yes, that's right. Actually, we are solving the problem of gradient noise. So we started from here. Came here. We came here. We came here. It's going. Everything is going right. But maybe once we come here, then it might be the case that this batch is noisy batch. So everyone is bad here in this batch. Now what will happen? If I go with the SGD, now since everyone is bad here, so it will give you the wrong gradients. And if you are getting the wrong gradients, your W will be diverted. So you are like going in this way, and your goal was to reach here. But what will happen? Now this will divert you, maybe in some other direction. Okay. Again, next time maybe you could be having good guys and good batch, and again it will try to face this thing on the original path. But again, it will take time. So your convergence will be slow due to this noisy batch. Okay. But if I go with the SGD plus momentum, so in the case of SGD plus momentum, I'm not going to rely only on the current batch. Instead, I'll also take the average gradient of the past. That is running average, like weighted average gradient of the past. So that means it's giving the actual direction here. So whatever past guys they were doing, from that we are just finding the average. So this average will give you some value. And then you are also adding the current batch there. We know that the current batches is having all the bad guys. But since you are not going to fully rely on the current batch, instead you are taking the help from the past also. So what will happen here? Again, it will give you the wrong gradient. But this gradient will be added in the past gradient. What you have observed in the, for all the past batches, the average of that. And then you are summing these two terms. So once you do it, and once you change the W here, again, there will be the effect of this bad guys, but it will be not that much effect. It may divert, but maybe only till this point. And again, you can come here. So your diversion will be it will be lesser compared to this case when you have gradient noise. Okay, so this is for the reducing, for overcoming the gradient noise issue. Did you realize it? Okay, so this is the formula for finding the average gradient. So here we generally take rho equal to 0.9 or 0. So that means we are giving 0.99 weightage to the previous past information and 1 weightage to the current information. So it's like just the formula for finding the the weighted average. So 0.9 is getting multiplied with this, and 1 is getting multiplied with this, and you are getting the average of this past and this current. Okay, so every time you are finding the average, and average is
So one question.
going to, yeah.
Yeah, sorry to interrupt. Since there is W1 and W2, consider W1 lies on positive axis as well as the negative axis. So what is the safeguard that we are doing so that it does not go completely in opposite direction? For example, if I am taking minus, my value will go on decreasing, but that is not something that I want. So how can we safeguard it?
No, decreasing means like at the end it should help you in like for finding the score function and loss. Okay.
No, no.
So
What
whatever
I mean
values
that
you,
VT1 is minus 10, and I again compute it, and I get VT2 as minus 20. Okay, so that is not right. But if I just add it, it is going to be minus 30. So that is greater than minus 10. So I'm going in opposite direction now. Eventually, I will come to local minima, but my time or iteration is getting wasted there. How can I safeguard it?
okay, so you're saying that maybe if you're getting this VT something minus 10 and this is giving you minus 20, and then you are summing it and then you are getting minus 30 again, it will give you the. So again, this the direction, because you don't know whether you need minus negative direction or you need positive direction. But since like just observe, like when we were just discussing the numerical gradient, then what we observed that when you have the negative gradient, that means you need to change in a positive direction, the plus that should be like there should be summation there in the case of W. If you have positive here, then there should be negative there, like just negative step. So that we already have observed. So that's why here we have the negative here. So it will make the term, if the term, the gradient term is positive, then it will make that negative when you are taking the step. So these all the things we already have discussed in the previous class. So actually it will not affect that. Okay. So actually it will like since you are giving the focus on the past, and past is the past average is something which is helping you to move towards the global minima or towards the loss equal to zero or close to zero. So this is like good guy. This is the good thing because it's not coming from only one batch. It comes from considering all the previous batches, like weighted average of all the previous batches. So we have to somehow rely on this. Okay, and then this may be the wrong information. So, but since this much right information you have, so again, if you are adding this much wrong information, still it will be better than this because here you will be adding all the wrong information only. Now, in this case, you have this much right information, this much wrong information, and if you find the average, then again it will divert you, but not this much. There is no guarantee that it will not divert you. It will divert you. But here it will diverting you a lot. So somehow we have decreased that or like reduced that diversion.
Sir, when we multiply the row value with the 0.9 and 0.99, for each and every iteration, the value of the VT, the value of the multiplication factor rho into VT will keep on reducing for each and every iteration. And the time will come where the rho into VT will be 0. At that time, what we need to do?
Yes, this is a very good point. So what sir said that if we 0.9, but again you have to also think about this term. So again, this is the past you got. This VT is the past information that you got, and you multiply this VT with 0.9, and then you are also adding the current thing, na? Next time this will be the VT.
Yeah, next time that will be VT. Okay.
So actually, it is doing the same. Like it's just giving more weightage to the recent past and less weightage to the old past batches. Because every time like you are multiplying with 0.9, so now this time it has got the weightage of this like 0.9. If I write 0.9 into Vt plus maybe I should write this fxt. Now next time it will be Vt plus 1, and again next time we'll be having Vt plus 2 equal to rho of Vt plus 1 plus again del fxt. So this time again you are multiplying 0.9 here. So this term will be 0.9 into 0.9, that will be 0.81, and this will be 0.9 fxt. That means the old, now again you are reducing the weightage to the old batches compared to the recent batches. So this got 0.9, it has got 0.81 in the next batch.
Okay, sir.
Yeah, this is happening iteratively. So this is the way of finding the weighted average. So actually this is the formula for finding the weighted average. There is no another formula. Here only it's getting happened. So every time it's giving weightage to the past and current, and then it's finding that. So this is the only formula for finding the weightage, this average, because it is going in a iterative manner. Are you able to realize it? Anyone has any question here? If you have question, please ask.
Now, where is the end limit for this one, sir? It will keep on happening. Where is the end limit until we get that W reduced to zero?
When you'll be happy, then maybe happier case would be where, like, suppose you got your loss very close to zero. That may be the like, and you just found that now your loss is not getting changed. So you got stuck somewhere, and loss is also very low, and now nothing is getting changed. Then you may stop there. So again, you'll write the stopping criteria. So most of the time you'll write, suppose you just observe 10 or 20 epochs, and if there is no change, you can stop.
And this is applicable for the image classification.
This is applicable for any type of problems.
Okay. But we are only discussing on a matter related to image.
Till now we have only discussed image classification. But once we go for the RNN part, then we'll also discuss for the text type of things. So it can be applied for any type of problem, and in every problem you'll be applying this type of techniques, and again it will work everywhere.
Okay.
Let me just tell you, like here, whatever I'm explaining in the code, it's just like one line you have. So ZD is just like, if you go to use PyTorch, you'll be having only one line. Just like Adam, import this NNN, like neural network from the PyTorch, and then use one function, like one class as Adam. That's all. And just put the parameter, that's all.
Okay.
So no need to write all the things, all the complex stuff. This is just for the sake of understanding how the things are going on. Otherwise, coding wise, it's very, very simple.
Okay.
Sir, could you please re-describe what this learning rate is doing?
Yeah, I'll come to this. We have one more slide for this learning rate. So I'll come. Again, we already have discussed this. Learning rate is like controlling the speed, controlling the change. So like when I was discussing this, when I had given the example of this numerical gradient, that time we had tried to somehow get how this alpha is working. But again, I'll just tell you, alpha is just learning rate. It's like it's just like a step size. What is the jump that you want every time?
Okay, got it, sir.
But you could refer to the previous lecture. There we already have explained in a great detail. And again, we have one more slide also for this, like how to fix it. That is also the challenging thing. Okay, so if this is clear, then I'll go for, like, we have somehow tried to solve one problem, that is gradient noisy problem. Now you can write the code by this very, very easy. So this was the code for the SGD. Take W, find the gradient dW, and then you, like here we are taking X for like in the place of W, So dw equal to compute w, and then we'll be having this formula. This is the SGD formula, w equal to w minus learning rate LR into gradient. Okay. Now in this case, again, this is the Python code, simple Python code. But let me just tell you, you are not going to write this code when you are designing any neural network. These all the things are already inbuilt there. So SGD plus momentum is already there. Just one line code, just take it. You don't have to write these all the stuff. But again, if you want to learn from the scratch, like how the things are happening, then maybe you can also write these all the algorithms from the scratch, just writing using Python, NumPy things, and like putting all the steps what we have discussed. Okay, so this is like compute X, that is like current gradient, and then you will be having this formula that we have already have seen here. So rho term, again, rho term is like hyperparameter because you are fixing it. This is also called friction. So how much friction I should give to the past. Okay. So this is friction into Bx and plus the current gradient. And then again, you are applying the same formula, what we have seen here.
Sir, as we are giving momentum to our optimizer, there might be a chance that optimizer jump or cross the global minima due to the momentum.
No, actually here we are momentum is something just we are also taking the help from the previous velocity, how the things were happening in the past. That is your momentum. The average thing that you are taking from the like weighted average of the past gradients, that is giving you momentum. So momentum is like helping you to keep you on the same path, because you know that some batch can comes and it may divert me from the actual path, like this what I said here, you can divert you. Now momentum, that is like your past information, which is momentum. So the past gradients, average gradient is your momentum, because that due to those past gradients you have changed your W. Okay, now you are taking the average this running average of that, and then with the help of the past and the current you are taking the decision. So I don't think that it will you can like it will overshoot. That's not possible here, because it is somehow you're helping you to keep you on this path, because current batch can divert you from the path, and it maybe you can go in this side. Now due to this past information and the current, now you will be at least again you will be diverted, but not that much. So if you are not, that is not, if the diversion is not too much, then you can come back easily in a short time. So it's not, I don't think that's related to the global minima stuff, like it will jump and like that.
Sir, but what if the depth of global minima is too low?
Depth of the global minima is too low. No, if you have this type of problem, then no need to use deep learning. If you have convex problem, that means you can go and you can reach here. You know, like you know the function. You can just find the gradient and you'll get this point. Then no need to apply anything. Then no need to apply any optimization algorithm. But the problem is like you do not have given this. This is not given to you. This much simple problem not given to you. The problem is like this. It's a very complex problem. So if the problem is simple, then again, in that case, maybe you can overshoot, but I don't think that, because again, your learning rate is also there. So many factors are there. So I don't think that it will overshoot. But again, if it is getting overshoot, then you have to somehow reduce something. So maybe you can reduce the learning rate. So you just make the speed slow. Because learning rate is something which will control the step size. That means like your speed. Your learning rate is also controlling this. Again, we'll talk these all the things later, okay? But I don't think that it will overshoot. Because if it is getting overshoot, suppose you observe that it is getting overshoot, that means your loss is fluctuating a lot. Then maybe you'll change the learning rate so that next time it will not overshoot. Did you get the answer now?
Yes, sir.
Okay. Okay. So now the next optimizer is RMSProp. So RMSProp, what RMSProp does, let us first see the SGD plus momentum. So SGD plus momentum is this. Now SGD plus momentum is like taking the average of the past and the current, and then just adding these two terms. That was the goal in the case of SGD plus momentum, and it has solved the problem of noisy gradient. Now again, we know that we have two more problems that we need to solve. One is like this saddle point and this local minima, but that is like global problem. So whatever we are doing here, every case, the goal would be to reach to the global minima. So anyway, like whenever we are optimizing, our focus is to solve the local minima and the saddle point problem. So those type of problems are not going to solve explicitly, but it will happen implicitly every time whenever we are changing something in the algorithm. Okay. So that means now we're not going to tackle that problem because that will happen implicitly. Even when we solve when we come up with the SGD plus momentum, that is also somehow solving the problem of this local minima and saddle point. So it is happening implicitly. Now only one problem left, and that problem is what? In one direction it was moving fast, in another direction it was moving slow. Poor conditioning problem. So your RMSProp comes with the solution which will solve the problem of poor conditioning. So what it does, it finds the square value of this past and current. So it is also similar to the SGD plus momentum. But in the case of SGD plus momentum, we are finding the mean, like average. Here we are finding some type of, we can say, variance. So we want to see like what is the variance in every direction. How fast the things are changing, or how the values of the gradients are what we say non-uniform. Because if this is uniform, that means if everyone is having the similar value, then there is no problem. Because in that case, in every direction, we'll be having same update. But the problem was that we could be having some direction. In one direction, it's very drastic change. In another direction, there is no change. That means in one direction, your gradient is coming very high. And in another direction, your gradient is coming very low. And due to that, there is no uniform change in the W. So this RMSProp come up with the idea. It comes with the idea that I'll make every direction, every change on the same page. That means after applying this, whatever I'm going to propose here, after applying this, every direction will be having, or every gradient will be having similar value. Okay. So what it does, it finds the dx is again your current gradient. It finds the square of the gradient, the current gradient, so dx square. And then it also finds the square of the past gradient, past average gradient. And then it finds the average of this. So decay rate is multiplied here, and 1 minus decay rate is multiplied here. So just giving some weight to the past and some weight to the current. In the previous case, we were giving one weight to the current, but here like actually we are dividing the weights from the 1. So we assume that we have total weights 1. We are giving some weights to this and 1 minus that weight to this. Okay. And now this is giving you the gradient squared. So previous case we were getting gradient the average of the past gradient, the average of the gradient. Now here we are getting the what we say the average of the square of the past square of the previous gradient. We are working on the square space instead on the original space. Okay, so this is just like finding the variance. So you might have studied this mean and variance. So in the previous case we were finding the mean. Here we are finding the variance, and then we are dividing that variance, or we should take standard deviation, because if you write something x minus mean divided by standard deviation, so standard deviation is what? Root of variance. So we are taking that variance and then finding the root of that, and then dividing this thing, then we are dividing this current gradient by this. So what will happen? Yes. So in the case of RMSProp, what we are doing, we are finding this current, we have the current gradient. So you know that current gradient is what? It's like matrix. We have 2D matrix. This is the 2D matrix that you got. Just this is the gradient del W that you have got. And then in the case of SGD, what we were doing, we had the W also, the same dimension W, and then we were just subtracting it, minus of alpha. Okay, this was happening in the case of SGD. Now here what we are doing, we are not subtracting this as it is. Instead, we are dividing it by this term, the square of this under root of gradient squared. Now what will happen? Let me just tell you. Suppose in this gradient, maybe we have one value is 100 here, one value is 2 here, one value is like 500 here. Okay. Now maybe you could be having some value, maybe maybe we should take 0.1 here, or maybe 0.2 here. Okay. Now if I like when I say this square, so I'll take the square of this current. This is the square of the current, and then the square of the past. So if I take the square of the current gradient that I have calculated, then if I have higher value, if I have high value, suppose this is the high value, this is the high value. So if I have high value, that value will be higher, because 100 square will give you 10,000. So if I take the square of this, I'll be having all the high value will be higher. So 1,000, 10,000, then maybe 2,4, then 5, maybe 25,000, and all the lower values means like it's close to 0. So suppose I have 0.1 or 0.2 or maybe 0.9, and if I take the square of 0.9, it will give you lesser value compared to 0.9. So now I'll be having like 0.9, I'll be having 0.81. Or 0.2, this will give you 0.04, or 0.1 squared, 0.001. So what is happening? Your large value is getting larger and your small value is getting smaller. Okay, and this will be done for the past also, because here like you're taking the current, this is the current one, this is the dW into dW, and this is the past one. So you are doing this thing for the past also. So if you do this, if you just do the summation, and finally if you get this W, this W will be having the value, it will be having the values larger, like compared to this. I'm just talking about this. So it will be having the values at the point, it will be having the values larger, suppose at this point, but before this value was only large. So previously it was only 2. Now it became larger than 2. And it will be having the value smaller, which was small in the case of gradient, the current gradient. Okay. So now you can observe here. So your larger value is getting larger and your smaller value is getting smaller. Okay. And you're just taking it and finding this under root of this. Still, whatever matrix you will be getting here, in that matrix, if you're getting 100 here, this will be having, at this point, it will be having maybe 150 or maybe 200. So if you compare this matrix and this matrix, in this matrix, if in the cell or in the indexes like this indexes, so where you were getting all the larger value, you were getting all the large value. Now you have larger value at this point. And wherever you are getting small values, now we have smaller values here. And if you divide this with this element wise, so what it will do? You are dividing, suppose you are taking this. So this is the large value, 100, and you are dividing 100 with the larger value. So it will give you a small value. And if you have small value here, maybe 0.1, and you are dividing with the smaller value. So a small value divided by a smaller value will give you large value. So 0.1 divided by 0.001 will give you maybe 10 or 100. Okay. So now you can observe here. What we are doing, we are making the small value large and we are making the large value small so that everyone will be on the same page. So purpose of this is to make everyone on the same page. And what that means? That means make every value similar so that there will be uniform change in every direction. Okay. Now I'll stop here and I'll.
Sir, that matrix portion, I didn't got the last portion which you just explained.
So what I was saying that like the problem that we were facing in the case of SGD was this. Like maybe in one direction I was getting like great change, in another direction like I was getting small change only. Okay, so these are all the directions in the W. W, like this is the, like you can say, a gradient. This is the gradient that you got. And again, you know that gradient is one matrix, na? Because your W is also matrix. So now this can be seen as a direction. This is one direction, this is another direction, this is another direction. So if you'll be having the same dimension W also, and then you will be applying minus of alpha this, and then you will be changing element wise, na? Your W is getting changed element wise. So this minus alpha into 100 will give you one new value in the W. Similarly, this minus alpha, this will give you another value in the W, and so on. So that is your new W. Okay. It's happening element wise. Now the problem was like there was no uniformity here. So in one direction it was giving you 100. That means great change. In another direction it was giving you 0.1. It's very small change. And due to that you were getting the problem that we were facing, the poor conditioning. So why not we should put everyone on the same page? That means why not we make everyone similar? So making similar, what we are doing, we are dividing by this term. And what this term is doing, if you calculate this term, the value for which, value for which we have large number here, suppose 100. Now if you find this term, it will give you the even larger value here. Maybe it is 100, then you will be getting maybe 300 or 500 at this point by calculating this. And wherever we have small values, you will be getting even a smaller values. So we have 0.1, suppose I am getting 0.001 and like that. Okay. And now you're going to divide this term by this term. It's just like you're dividing your the value with the variance. So this is the variance. How like how fast it is getting changed, and you're dividing your value with variance, or we can say standard deviation, because we take the under root of variance. So wherever we have large value here, and if you are dividing by even larger value, this will make the value smaller. Are you getting my point?
Yeah. Yes.
And whenever we have small values, and if we are dividing by the smaller values, then it will make the value large. So 0.1 divided by 0.01 will give you large value like 10 or 100. Or maybe in this case, you'll get 10. So what is happening here? Now we are making everyone to come on the same page. So we are making this matrix uniform so that everyone will be having the similar change. So this is like we're trying to solve the poor conditioning problem. Now is it fine to everyone?
Yeah. Yes, sir. Now got it.
Yeah. Anyone has any,
But it will increase only if the number is between 0 and 1.
Yes. So we also enforce while applying this regularization term, because regularization is also, it's like here, like I'm just talking about this component, but regularization will also come. So regularization will also take care of this thing. So between 0 and 1, like that. Again, I'm just giving you the example. I'm trying to convince you like how it is happening. But in reality, this works well. Okay. So this is whatever values we have, it will make everyone on the same page. Did you get the answer or not? Just for the sake of explanation, I have given 0.1 and 0.2. But in reality, you'll be having different type of values. And again, this will ensure, this also theoretically ensure that everyone will get the similar values. Not exact value, not same value, but similar values. Again, since you know that whatever new algorithm is coming, that is also having some limitation. So it's giving the pros part, but it's also having some cons part. So it's not every time you will be giving the perfect model. That's not guaranteed. Even in any type of optimizer, that guarantee is not there. Okay, so did you get the answer, or still you have like confusion? You are in confusion.
Sir, got it. We just need to go through these slides once. So
yeah, please go through it. But this is just like I've just given the analogy, like how it is happening. Okay, so from top I've just given you, but again some mathematics is involved there. But so there's the same thing is happening there, and the purpose is same only, to make everything to put on the same page.
Basically,
Okay, so
RMSProp. So will make learning rate effective, right?
Learning rate is like it's giving equal weight to everyone, because alpha is like one value. It's like a scalar values. So this is getting multiplied with everyone here. So it's like giving uniform, like same value to everyone. But you know that due to poor conditioning, you could be having maybe more higher value in one side, lower value in another side. And that can create problem, like it may slow the convergence. So that's why we want to change every individual value here to put all the values in the matrix on the same page. So like adaptively, we are changing every value here. Your alpha is also doing this. It's also changing it's also like changing the value here. But it's getting multiplied. The same value is getting multiplied with every value of this, and that's what the problem. So alpha you can take. Alpha is like it's like global control, but you could be having local control also. So that local control is happening through this RMSProp. So it's like global speed, and this is like local speed. Like you are just changing the speed in every direction. Now is it fine?
Yes, sir, yes, I got it.
Yeah.
Sir, how does it help in reducing the losses by doing this, by following this methodology, sir?
Loss, it's like you're changing the W, you're moving towards the we can say optimized W, that, or we can say like the better W. And you know, like whenever I'm saying better W, that means my loss would be less. So that's the purpose. So SGD is coming from the SGD only. At the end, you are using SGD only, and you know how SGD is working. So it's every time it's giving you new W, which is having lesser loss compared to the previous W. That is the purpose of the W. So in that way, like it is reducing the loss. So this is happening for n number of times. So every time like you started, you're just moving in a W space. You're moving in a W space. You started from somewhere here. Now your optimizer is the helper, which is helping you to fetch you towards the loss equal to 0. So every time it is helping you to reach close to the L equal to 0. So next time you will be more closer. Next time will be more closer. Next time will be more closer. Next time will be more closer. So whenever you are applying this algorithm, you will be more closer to loss equal to 0. And that you are getting W by multiplying Wx and then applying the loss function.
Okay, sir.
That means we are moving towards the happier case. So at this point, we were unhappy. And then we are slightly moving towards the happier case. Happier case means your model is going to the expert. That means it will give you accurate result most of the times.
Okay.
Okay. So I think then I'll stop here. In the next class, we'll see the Atom. That is the next optimizer, and then we'll also try to touch some like learning rate, and then this part will be done. Then we'll go for the fully connected network. So fully connected network followed by this back propagation.
So only those three problems that we come across, or do we have any other problems? Like for example, you spoke about gradient noise, and you spoke about poor conditioning, and you spoke about local and global minima. Only those problems do we have, or do we have any other problems in the?
These are like major problems, but you could be having other type of problems also. But these are like major problems that we generally face when we go with the SGD. Actually, let me just tell you this. Minima, local minima, and this is like global problem. Saddle point and local minima is like global problem. So it's applicable for every type of algorithm, whatever you are doing. So every algorithm, the job of every algorithm is to somehow come out from the local minima or saddle point. Okay. So that is like the common problem. But this gradient noise and this poor conditioning these were the problem in the case of SGD. And then again, these were like main problem in the case of SGD. And then these like all the new approaches came and they have solved these problems. They have not solved, but they have tried to overcome this problem. Later again, you can find out a lot of maybe more than 500 algorithms which came after this SGD, and they have worked in a different dimension or different direction. So they try to solve different type of problems. Suppose even Adam is also having, even RMS is also having problem. So everyone is having problem. So whatever algorithm is coming, it will be having pros. Like it will solve some of the issues of the past algorithms. But again, it will also having some new problems. And for those new problems, you can again deep dive. You can try to develop new algorithm. So maybe next time you can also come up with one new algorithm that may solve the problem of the recent algorithms.
Okay, sir. Sure.
This is like evolving area. So a research area. Okay. So I'll stop here and thank you. In the next class, we'll cover this. Let's try to complete it.